So now I would like to introduce the next speaker. Next speaker is Dr. Hannah-Noa Barad. And the title of a presentation will be Combinatorial Material Science for Improving Contacts to Halide Perovskite in Solar Cells. Just let's wait 2 seconds for technical reason, and then we will start.
So thank you very much for the introduction, and thank you for having me here. So far, this has really been a great conference, so thanks very much for the organizers. So today I'm going to talk a little bit about our lab, what we do in our lab, and how we've implemented this for perovskite solar cells. And I'd like to start off, So I'd like to start off a little bit by giving you an analogy for our motivation and why we work the way we do. So I'm sure all of you know who these two people are, Donald Trump and Barack Obama, previous president of the United States and current president of the United States. But have you ever wondered what would happen if we tried to mix these two people together? I'm sure you didn't think of this, but we do this every day in the lab. So when you try mixing them together at different ratios, you get a variation between kinds of different people. And in the end, you end up with some sort of, in this case, a 50% mixture of this kind of neutral new president. So he's got a little bit of a wider face and scrunchier eyes than Barack Obama, and he's got darker hair than Trump, but okay, I mean, it's a new kind of mixture, and this is just the 50% mixture. Now, let's say we have some political issues and the president gets into a heated argument. So what would happen if we would heat things up a little bit? So some people get mad and some people are just not affected. So in that case, when we look at our 50% mixture, we have this sort of grouching kind of new president. So he's not that happy as compared to the original neutral person. And then sometimes in politics, there's pressure. So we have pressure from different countries and the UN and things like that. So what would happen if we apply some pressure on these two presidents? So some people don't care about pressure, and some people work really well under pressure. So they're quite happy to have pressure. In that case, if we look at the 50% mixture, so we get these, suddenly we have this new feature of teeth showing, and we have wrinkles around the eyes. So all of these three mixtures, and these are just the 50% ratios between both presidents, have completely different features. So the analogy would be that materials and devices, their structures, minor changes really affect the way we see the materials, the way they perform, their characteristics, the devices, and even sometimes their underlying mechanisms. So that's why in our lab we work with combinatorial materials science. And what exactly is combinatorial materials science? Sometimes people think it's a method for optimizing certain devices or certain materials, but in fact it really isn't. It's a whole cycle of different steps and different levels. So you start out with fabrication of a material device or libraries, and originally one of the most famous combinatorial studies was done by Wang in 1998, and he found new phosphorescent materials from a combinatorial study. So this really has proved and has worked. So the fabrication is really important. And a library would be basically one single substrate with multiple materials or multiple devices on it. Then the next step would be high throughput analysis and characterization. So you have to characterize each and every single point on this library because each one corresponds either to a different material or a different device structure. The next step would be computational analysis and modeling, and obviously all of this information from the fabrication to the analysis and measurements are all saved in a database so that we can later extract this information and apply machine learning, genetic algorithms, some computational analysis. I'm sure most of you have heard of AFLOLib and the Materials Genome Project, which are the complementary computational methods for finding new materials. And they do many calculations, and their databases are open and available online for people who are interested and want to look into them. And eventually what this gives us is design of new experiments or new materials, and these materials don't always necessarily have to fit our application. So for instance, in our lab, we do photovoltaics, but could be that some of the materials we discovered are actually better for LEDs, for instance, or any other thing. So it really isn't limited, and it's quite diverse, I would even say. So in our lab, we have two basic structures. We have combinatorial material compositions and combinatorial devices for material absorbers, or not necessarily material absorbers. It could be back contacts, as we've now started, and I'll show you a little bit about later. So what we do is we usually form continuous compositional variations throughout the library if we're looking at a new material. We can also vary the layer thicknesses, and this is just an example of a binary system, but we can do quaternary, etc. So basically we can control what the deposition shape will look like and the ratios between the materials. And then this would obviously form different types of phases, new materials, new amorphous materials. Anything is interesting for us. And then we have the combinatorial device libraries. So in this case, we can have layer thickness variations, combined it with the material composition variations, and we can even have up to 676 solar cells per library. So this is an example of one of our libraries. They're about 7 by 7 centimeters in size, and each single point over here is a different solar cell library, solar cell sample. So this is one library with 676 solar cells. Our standard is 169 solar cells per library. And if we put more back contacts, in that case, we'll have more solar cells. So the fabrication methods that we use at the moment in the lab include spray pyrolysis. So this is a system that we designed and built up. And it can linearly spray different thicknesses of materials and different compositions. We can also use this for homogeneous layer depositions. We have pulse laser depositions, so we use this on our large area substrates, and we can have up to 6 different materials inside our chamber and deposit them sequentially. We also have RF sputtering, and we can use up to 4 sputtering power sources simultaneously, so 4 materials potentially, but obviously this varies because if we use target materials that have more atoms inside of them and more different materials, then we'll gain more complexity and more information. As for our characterization tools, so we built most of them in the lab because obviously usually you don't get these automated systems. So we have optical spectroscopy, IV characterization, EDS, IPC, resistivity, Kelvin probe and surface photovoltage, impedance spectroscopy, XRD, Raman, Seebeck contact angle, and most recently, since we've started implementing perovskites in the combinatorial setup, we have photoluminescence PL imaging that is now under construction. So we're really moving towards the perovskite materials. Originally, the whole combinatorial setup actually started out for oxides, so now we're moving it to the perovskites. So here are just a couple of our scanners and the way they work. So they really go point by point, and they scan each and every point. So some of these are actually sped up because it does take a couple of hours to scan resistivity. It's not this fast. The IV is pretty similar to what it would be. So usually it depends on the scan rates that we set, but any of the measurements can take up either half an hour and up to a couple of hours. For impedance spectroscopy, I would say sometimes a week, but obviously that's a slow scan, so makes sense. So this is just sort of a summary slide, and it even doesn't include all of the measurements and options that we can do in our lab. So everything is interconnected, and literally we have thousands and sometimes even millions of data points for all our libraries together. And today I'm going to focus a little bit on some of the IV measurements that we've done and some of the optical and thickness measurements. But you can see that it's really very diverse, and we've built all our systems ourselves, so we can always add new things and new calculations, new measurements, things that we're interested in or other people who want to collaborate with us are interested in. Okay, so a little bit about what we've done with the perovskites. So considering the fact that originally our combinatorial project started for oxides, we've only about, I'd say, 2.5 years ago started using it for perovskite solar cells. Until then, we just had regular perovskite setup. So you can see this is a large area device with perovskite deposited on top, and this would be the cell structure in this case, so it's a mesoporous structure. And originally what we tried to do was figure out how to deposit a homogeneous film on such a large size, because spin coating is not so simple and straightforward, and it definitely usually doesn't give such a homogeneous layer, especially for these large size substrates. So this is just a reference library that we prepared. So you see a pretty homogeneous VOC, but the current and fill factor and as such efficiency are not quite as homogeneous as you would want. So what we did in the lab was we figured out that using a methylammonium iodide vapor treatment at varying temperatures, we were able to actually increase the homogeneity. So this is after the two-step deposition, and then we treat it with the vapor. And what we end up getting is that different temperatures show different responses. And the methylammonium at 140 degrees really gave us a very homogeneous layer. So you can see efficiencies between 12 to 16%, and very high nice currents and nice voltages, about 1.1. So really throughout the library, we are able to obtain a homogeneous layer, which is very good, obviously, because we want to then examine the different back contacts and see how they affect the perovskite layer. And obviously, if we don't have a homogeneous perovskite layer, then we can't really compare between the points. So this is the next step that we did, understanding what the compact layer of the TiO2 and how its thickness variations affect the perovskite solar cell. So again, it's the same mesoporous setup, and you can see that we have a linear gradient. I hope you can see. I don't know how the graphics are from far. We have a compact layer of TiO2 with a linear thickness gradient, and the thickness variations were from 20 to 600 nanometers. And I should mention this wasn't for a given library, so we had like a few thickness steps in order to obtain all of these thickness variations. But in the end, over 800 solar cells were analyzed for this specific study. So you can see the different thickness effect of the compact TiO2 on all of the solar cell parameters. And what you can really see is that in general, the VOC isn't affected that much, not shocking. And the current is actually quite affected. So above about 350 nanometers of TiO2, we get a really major degradation and also a lot of dispersity. The fill factor is obviously affected, and the efficiency goes down as a result. But you can see that there are some areas of the current which have quite high current, especially for the very thin areas of the TiO2. So what we did was we figured out that basically the only changing thing in this library is just the thickness of the TiO2. So we were able to calculate the bulk series resistance and the shunt resistance of the TiO2 layer and fit it using the diode equation. So basically you can see quite a nice correlation in the thinner areas of the compact TiO2 layer. And using that fit, we were able to optimize the thickness. So the thickness that would be good for the perovskite cell, in this case it's just MAPI, would be 50 to 300 nanometers for the blocking or compact TiO2 layer. And the highest efficiency that was obtained was for the 50 nanometers. Now, using these models, we were actually able to predict an increase in efficiency of about 1 to 1.5% for lower thicknesses of TiO2, so about 30 nanometers. We did have those in the study, but it's important to mention that at those thicknesses, the way we deposited the compact TiO2 was by pyrolysis. We actually don't get a very compact layer. What you get is small islands and pinholes, which obviously affect the photovoltaic performance. So if we were able to form thinner layers of this compact TiO2 and have them actually be homogeneous layers with no pinholes, then we would probably see the increase in efficiency that is predicted. Here are some really preliminary results of something that we just started doing about, I would say, 8 months ago or 7 months ago. So we're now looking into the hole transport layers, so inverse cells or PIN cells. And in this case, we're varying the thickness of the hole transport layer. We chose nickel oxide as a case study to begin with. So what you see is that the top part of the device, if we look at the top, at the sample from on top, is where the thicker nickel oxide is. And the variation in thickness is from 5 to 80 nanometers. So the bottom part is about 5 nanometers and the top part is around 80 nanometers in thickness. So if we look into the absorption, this is just, I took a bunch of points down the center. Oh, sorry for the very low resolution here because of the projector. But if you just look from the top to the bottom, you can see quite high transparency in the visible region. Basically, this is very good for us. We don't want it to absorb. And so even for the thicker layers of the nickel oxide, it's very transparent. So here are just the maps of the photovoltaic characteristics. I want to remind you again that the red indicates the highest values. So if you look over here, we get quite a nice VOC throughout the library, about between 0.8 to 1. So this is like one of the first attempts that we had with this material. It's not really optimized, and the fabrication isn't optimized either. We get quite nice currents and overall efficiencies of 12%. But the 12%, as you can note, is really for the thicker layers of the nickel oxide, which would indicate to us that we might need to go to even thicker gradients of the nickel oxide layer as the whole blocking or conducting contact. And in that case, maybe we would get even better performance. But this is obviously work that we're doing at the moment. So these are just some sample IV curves so you can see. This is from the thick nickel oxide side and the green is from the thin. So you can see there's very minor hysteresis. And this is really seen throughout the library, this kind of behavior, and very rectifying, quite high fill factors. So it really does work. It's not made up. And another thing that we've just recently tried, like 2 months ago, we've only started, so I barely have any analysis for this. But this is a binary deposition done by sputtering between copper and nickel oxide under oxygen flow, so reactive sputtering. And basically what we were trying to do is see the different whole transport layer as an effect of different compositions between the copper and the nickel. And we were trying to form the dilaphocyte structures, but at the moment we're not sure what we have because we haven't analyzed it yet. But you can see that there are variations in compositions. So we get about 0.6 on the top part for copper and about 1 down at the bottom for the nickel. So not exactly a 1-to-1 ratio, but still an interesting ratio between the materials. And obviously, we're going to look into this and see what phases we have over here and how they affect the photovoltaic behavior, which hasn't been studied yet. So just a bunch of take-home messages from this presentation. I hope I convinced you that combinatorial material science is useful and an important method for understanding solar cells and I guess materials in general. We are able to tune and understand the electron contact in the perovskite solar cell. We're also now looking into the whole conducting layers using combinatorial methods, and obviously our future plans are forming many compositions of perovskites and different cations, mixed halides, things like this. And obviously we're open for collaborations. If anyone has any ideas, wants, capabilities that they're interested in, we're really happy to collaborate. I would like to thank the leaders of our group, Professor Ariet Saban and Professor David Khan. And this is our lab. Most of the work that you saw was done by Laxman, Kevin, Ilana, and Adi. So thank you to them for their hard work. And thank you for your attention.
Yes, thank you, Hannah, for a very interesting talk. Now we have time for a couple of questions. Yeah, David.
I'm sorry, Hannah, you said at the beginning that you didn't want to spin coat these because it was such a large sample, but I didn't hear how you put the perovskite down.
So we did spin coat it in the end, and that's how we optimized it. But we are now looking into different methods for forming the perovskite. So co-evaporation, which is a work that we're starting to do with Henk Polnick, and also sputtering.
And my other quick question is, for these combinatorial studies, I'm wondering if there was a issue of what the nearest neighbor spacing could be on your library before you started to get some sort of crosstalk between neighboring information.
Yes, and this was something we've dealt with a while back, so I would say several years ago, especially with the oxide devices that we've built. But at the moment, it's optimized, and there's a long enough, I would say, distance between them that there's not much crosstalk, so if none at all.
I thought the perovskite would have a much higher conductivity than the oxide, so I would have thought that you would have had to change your optimization.
So we did think that to begin with, but from what we've seen, not so much. And usually we use only one back contact per library, so the distance is a lot higher than what you saw because I mean, they're not as close together, so there aren't 4 back contacts.
Thank you. Other questions? So if no questions, let's send speaker again.